Hello, I'm Steve Miller. Today I want to talk about the contemporary challenges of connecting turbulence models, that is RANS-based ones, with time and spectral analytical acoustic sources to do aeroacoustic prediction. Here's an outline of my talk. I want to introduce the problem and the outcome, of course, and I want to talk about typical Reynolds-averaged Navier-Stokes models and their connection for aeroacoustics problems. And first I'll talk about the traditional connection, which is often used today to do industrial scale design acoustic predictions from existing industrial RANS turbulence models in CFD. I want to also talk about the outcome or alternate approach, which is becoming more and more prevalent, which is large ID simulation with the Fox-Winn-Hawking approach. Then I want to show you a number of recent developments from my group to predict noise based on analytical acoustic sources that are either statistical or in the time domain. And these will be small-scale turbulence, or fine-scale turbulence, if you will, shockwave shear interactions, and the elusive large-scale coherent turbulence model, which is an enigma in the acoustics community. And I want to argue that we will connect these to wave number spectra, where sort of noise is the fingerprint of turbulence. And if you can find wave number spectra somehow, you can directly find the noise. And that might be a way forward or need from the RANS community and the aeroacoustics perspective. So of course, in the turbulence community, modeling community, and aeroacoustics community, we have separate sort of research groups and goals, and we need to come together to do accurate acoustic predictions from RANS-based solvers, which is very practical for design. And it really means we need to make some empirical assumptions to make practical predictions, and it should be that we should try and eliminate empiricism to make more accurate predictions. The new approach of LES and Fox-Winn-Hawking's approaches has some downsides in that we're really learning nothing about the acoustic sources, but we're making some accurate predictions. It also has a huge computational cost relative to RANS. Here's the typical RANS models which we work with. We have, of course, momentum, Reynolds stress equation, dissipation equation, and TKE. And we might just also say, from an aeroacoustics perspective or a user of CFD, what is the output of the codes? Well, we know the geometry. We have the computational grid where we store variables from an acoustics perspective. We have the mean variables like U bar, V bar, P bar, etc. And we usually have two equation models. One equation models aren't useful for acoustics because you can't estimate length and time scales typically. So we usually want two equation or higher models from RANS in practical acoustic predictions. And you usually get K or omega or epsilon. And even better, you might use a Reynolds stress model and connect the Reynolds stresses to, say, the stresses derived from an acoustics model. So you get the Reynolds stresses in epsilon or omega. So that's what we have to work with, and we're usually just given that from like an industrial CFD database to find acoustics. The traditional path of acoustic analysis and acoustic predictions was found by Sir James Lighthill, and he did nothing but take the compressible Navier-Stokes equations and rearrange the left-hand side into a wave operator and put everything else on the right. And that's shown in equation 5. And he would solve this equation with a Green's function, and the inhomogeneous source is Tij, which is the Lighthill stress tensor, which is shown in equation 6. And so it's really an integral equation that convolves the source with the vector Green's function. And modern approaches that predict noise are based on this approach too, unless you go down the path of Fox-Winn-Hawking's. But of course, Fox-Winn-Hawking is also an acoustic analogy. Now, typically, when you model the double divergence of the Lighthill stress tensor for spectral density, you get a two-point cross correlation of this term on the right-hand side of 5. Well, when you do that, you have to create models for the two-point cross correlation because you don't know what they are because you only have, say, steady RANS simulations. And so you're assuming forms of two-point cross correlations based on the RANS output. And we would estimate time and length and velocity scales from that approach. Well, here we have a length scale, a time scale, and a velocity scale, say, of turbulence. And they could be frequency dependent, if you wish, and become very complicated. And that's what a lot of people's research has become these days, of how to estimate these from the RANS variables better. So this is the real connection. And the simplest one to make, you have 3 constant coefficients, CLC, tau, and US, and you just basically do a dimensional scaling of turbulent kinetic energy and dissipation to get like a length scale, etc. And then you have models for two-point cross correlations. Here's the model for the two-point cross correlation. For a spectral prediction of acoustics, you would have a source of the two-point cross-correlation of Lighthill stress tensor, the double divergence of it, and you would write that as, say, the fourth partial derivative with source time of Rijlm, which is approximated as the density times the two-point cross correlations of the velocities. You can see these terms in Lighthill's equation right here in equation 6 where my mouse is moving. So you can see the normalized two-point cross correlation model R. We have a normalized model for it with a magnitude is just an approximation to connect it to RANS. And all this is just a typical two-point cross correlation normalized model involving, say, 2 points from one particular point in the CFD. And this is actually a published model from AWA Journal in Chris Tam's work. Connects the length, time, and velocity scales from a RANS simulation to the CFD model. There's more contemporary acoustic prediction models like in equation 13. Here's one I created. This is more general than Lightill's approach and it's published in AWA Journal. You have the acoustic pressure at position x and time t is nothing but an integration of the Green's function over acoustic sources theta n. And here it is in the spectral approach. So you have x and omega instead of t. Here's the sources. The sources are nothing but the continuity equation, momentum equation, and energy equation, theta 0, 1, 2, 3, and 4, respectively. So if we know those, from, say, LAS, we can do a direct prediction with no assumptions. If we have RANS, we still have to connect these two-point correlations somehow with the outgoing predictions. For fine scale or small scale turbulence, we know what the sources are. And the sources are, say, the material derivatives of pressures, pressures with rho UK UK, and, say, rho UK UK with rho UK UK. We can approximate these and connect them to RANS like we did with the traditional approaches of Lighthill. We also have a time domain source for shockwave shear lunar action like in a jet flow, an off-design jet, and you can also write that in the spectral domain to go in the spectral model. Here's one example of these types of predictions. The red lines are experiments. The y-axis represents sound pressure level. X-axis is non-dimensional frequency. This is from different angles radiating from a transonic heated jet at a nozzle pressure ratio 1.9 and total temperature ratio about 3.2. You can see the predictions of the present model match the experiment really well. And this is from a steady RANS simulation connected to this contemporary acoustic prediction approach. A more advanced approach might connect the model to wave number spectra of each of the field variables like velocity, density, pressure, and temperature. If we could have a RANS type model that could predict these instead of finding these from LES, we could do a better prediction. Is it possible to create a RANS model that predicts wave number spectra of the field variables? If we did, then the whole problem would be much simpler. An example of this type of approach is taking a DNS of turbulence and comparing it to a completely theoretical prediction from inhomogeneous isotropic turbulence in the far field. This is one example that was published in the IAA by myself in 2016. The x-axis is Struhel number, the y-axis is sound pressure level per unit Struhel number, and the black line is the prediction and the red line is the DNS. There's also just a purely using wave number spectra from turbulence theory to fill in the values shown in 21 through 24. Models for large-scale coherent turbulence are completely elusive in the aeroacoustics community, and therefore we use Elias and Fox and Hawkins to make predictions. It's really up to the aeroacousticians to try and close the loop here. Let's look at some contemporary issues between RANS closures and aeroacoustic sources. Typically, RANS gives us Q bar, the field variables, and K omega or epsilon. And Reynolds stress is, of course, being connected to current models, which gives us better predictions. In aeroacoustics, we usually need a two-point cross correlation, as I showed, and different length scales like L and tau, which are estimated from RANS. And then we have to calibrate the empirical coefficients. Ideally in RANS, we would like to get direct wave number spectra of every field variable, or even better, some kind of idea what the two-point cross correlations are. It would also be wonderful to try and form RANS closures that yield results that are more directly applicable to the RANS community. In aeroacoustics, we need to formulate models that are more compatible with RANS to reduce empiricism. Most importantly, in the aeroacoustics community, we need to create models for large-scale structures that are dependent on turbulence statistics and mean flows. Otherwise, we'll never be able to create good predictions of noise from large-scale structure turbulence using RANS solutions. Thank you very much for your time today. I'm Steve Miller.